So I have started recording, and I think we are also transcribing, which is good. That means I'm audible. Let me share my screen, entire screen. Okay. I mean, I am sure you all must be seeing the screen. Audible. Okay, yeah. So this is from the screen mirroring of my iPad, and yeah, so we'll be using two windows. Yeah, one is the this basically Wolfram Alpha. Perfect. Okay, so let's wait for 5 minutes before we start. And yeah, so it is gonna be. So it's mostly about the yeah. So this week is mostly about the differential equations. That's the highlight of this, right? So if you just, I'm briefing before the students come because you can see these things on your videos also. So just to brief, what we usually do in our previous sort of things is uh, right, we have used nsolve to solve set of simultaneous linear equations. There is similar way to solve the set of differential equations. They could be coupled as well, and as much as possible, what kind of equations you have, you can do all those kind of differential equations using a command called dsolve. And that's what is the main command in order to solve the assignments for this week. Right. So that's the focus of our today. And not just that, so we will be dealing with various physical problems, like one which were discussed with you in the lecture by Professor Aditya Sharma of this course. So it was about the LCR circuit, simple harmonic motion, damped harmonic oscillator, and all kind of stuff you must have done. You have must have written the differential equations for all sort of things. And that's the idea. We have to solve some physical problems related to that. Even your assignments would focus on some physical results from this physical equation, which you can easily understand just by doing writing a simple code in the Mathematica. Okay, so there are many, many different algorithms to solve the differential equations. I mean, you would use the inbuilt solve to solve many of these, but you can be asked to perform a particular method like Euler's method, the modified Euler's method, and there could be many more, like RK4 and those kind of stuff. But our focus will be mostly concerned to the, I guess, modified Euler and just the Euler. That's my kind of focus. Okay, just a second. It's just the lighting. Huh. Yeah. So that's the main focus of the problems today. Okay, so this is just what I brief about what we are gonna discuss. So let's wait for another 5 minutes because if the student should turn up, then we can start solving these problems. For example, the one you see on your screen from the 2024. So let's see if I'm able to add a page after this. Hmm. Okay, yeah. I want to see if I am being transcribed properly. Right. I think, yeah, we are being recorded. That's fine. So I'm just waiting for another 2 minutes till it turns 3 p.m. Anyways, I have, discussed a basic idea of the this week. So there are usually 10 problems in your assignments for the course, and you're supposed to do them. And based on that, your score will be decided. So I'll be doing such problems based on the previous year assignment set. Now that can be, some of them can be same, but mostly it would be very different. Right. So yeah, we'll start the problems in just a few minutes. It's regarding, it's an initial value problem. Before we start, let me wait 1 minute to till it turn to 3. Yeah. Okay, let's wait another 1 minute. I think then we can just begin now. Fine. So this is the first problem. It's about solving the initial value problem, as you can see on your screen, given by this differential equation. And with the initial conditions, x at 0 is this, and x dot, the first derivative at 0 is this. So first I will just solve it for you in, the actual way we are supposed to solve, like in the um, normal maths you use to solve this. First, we are going to do it that way. And then we are going to solve this basically based on how this problem has to be solved on Mathematica. Okay, let's begin. So our differential equation is this. Okay, these are the initial conditions. Okay, now how do you solve this problem in general? In general, your solution you would assume as, okay. Now if I take the first hand derivative and second hand derivative, so that will be, give you the characteristic equation as r square. You assume it to be e to the power rt, let's say. So this is how it will be. So that would be our characteristic equation. Now this can have real plus complex power like this. So there would be, okay, so your x of t would be e to the power minus t by root 2 and cos, so c1 plus cos t by root 2 based on the second part. And okay, now that's one of the thing. Now next part has to be what? your initial conditions. So one, so gives you C2S1. Right. Okay. So this means your solution has to be okay. Now that you can always write cos A plus cos B as 5/4. This you can write, right? So yeah, so your solution will become okay. This is the solution if you derive it by your understanding, right? But now that's not what we wanted. We wanted to solve it uh, using the online differential equation tool. So let's do that. Okay, so this is your thing. Now we'll write the uh, problem using dsolve. Let's do that. So I'll define it in a solve, that is a solution. Dsolve. Okay, let's just look at it once. What does it look like? For example, assume that you don't know anything about this. Okay, so right. This is the way to solve the differential equation. What do they say? They say you have to write equation ux. Okay, if the differential equation is of the form, let's see the details. Yeah, so if the differential equation is of the form u bar x f of x comma u, this is how it will solve. I mean, this can solve partial differential equations as well and all kind of such equations, which is very good. That's what we have to do. We have equation, let's say in terms of x, um, x and x dot is equal to f of xy, then we can solve it in this way. So basically, first you have to write the differential equation. Okay, let's do that. So what is our differential equation? In the first curly brackets, you would do that. If you want to put curly brackets, if you don't, that's also okay. So x double this thing t plus, or you can write as equal equal minus x t minus sqrt 2 and x bar t with the conditions are x bar 0 equals 0, x 0 equal 0. Sorry, that is 1. Close it. What do you want? You want x of t, and what is the variable? T, independent variable. Enter it. It solved the equation. So it gave us e to the power minus t by root 2 and this thing. Now there is a way where you can actually solve this by the this thing, like if you want to solve it as a solution. Yeah, so one can actually check using Mathematica only. If this is the thing, first option, and here this minus dot sol 1, simplify. Let's try that, try doing that. So first option is what? Let's write that. x of t, whatever you have, dot solve 1 plus simplify. Should return me what? Should return me 0. So it didn't return you 0. Then you must have messed up something. And what is that? Yeah, so if I take it as just this, that will return me 0. It's option 3. Yeah, so that's the correct option, right? So that's how you should see things, okay? Fine. So this is how you solve the problem number 1, and these are the solution. Let's go to problem number 2. It's also a differential equation. Now, what kind of differential equation is it? It's the, let me add page after this. So it's with x of 0 as 1, t belongs to 0 to 5. Okay, now, right. So, okay, now let's solve this in general. How would you do that? Now, this has to be your solution, right? But let's do it the way using desolve. Okay, so how would you do this? Let's do the solve equal to d solve. Now differential equation is bar t equal minus xt into t. Okay. Okay, yeah, we have put the condition, so it should give me the correct thing. So it gave me e to the power minus t square by 2. Now let's plot this. So let me extract the solution out of this thing. Then we will plot this. So how will you extract the solution? It's xt x t slash dot first. It will give me just e to the power I square. Or I could have done this as well. It's the same thing, right? So if I do first, in both the cases, same thing. Okay, you have this now. Now I can plot this from t equal to 0 to 5. Plot xt comma t from 0 to 5. Yeah, you can do greet label and all that. I just don't want to do that right now. So yeah, if you see, this is like what function in your problem? It's definitely the problem option B. B is the correct one. Okay. Let's move to the, let me delete this empty page. Okay. So let's move to the problem number third. It's about dimensional analysis. We'll do it in a normal way as well, and we'll try to code it up in the case of like how can you just do without using your mind? How would you code it up in the Mathematica? Okay, so right. Before we start this, so this problem governs the dynamics in LCR circuit. And if you remember writing the differential equation of LCR circuit, you would see there are lots of time scales involved in that. And these are combinations of L and R and C, L and C. So basically these different type of time scales are there in your problem. So what we have to do is we have to identify these timescales out of these six options. Like from these options, what all are timescales? That's the number one thing. And we can do it simply by just writing the units of L, C, and R, and then finding out which option corresponds to the time dimension. Simple as that. Okay. So let's, instead of just doing that, let's first write only for L and C and R, and then rest we will compute with this thing. Let's do this. So L is clearly kg meter square coulomb minus square. So it's nothing but m L square q minus square. That's the L. It's inductance. Let's define it by L dem. And capacitance is c square by kg meter square. Okay, which is q square minus 1 L minus 2. Similarly, R is nothing but kg meter square per second, which is nothing but M L square Q minus square T minus 1. Okay, so these are the three things you have for in your problem. Now let's try doing that with Mathematica. Actually, why do we need to use Mathematica? That would make it much more complicated, right? I have given the code actually, but that's not what our intention would be to use. Okay, you can just do it by simple these options. Let me add a page. Hmm. Let's do that. Option A, L by R. Let's use the units now. It is M L square Q minus 2 by M L square Q minus 2 minus 1, which is T, dimension of T. So this is definitely correct option. So we can just look at the first thing, right? 1 by square root LC. Just look at 1 by square root LC. L is what? C we have to see, sorry. Are you sure? Hi, is someone there? Diksha. Uh, can you hear me? Can you turn off your mic and just let me know? Uh, okay. If you have any doubts, you can just ask me in the chat box, and or you can turn on your mic and just let me know. So I am doing the problem number 3 from the previous year assignment. So which is basically about identifying the time scales in the LCR circuit. Now, if you remember, if you write the equation of LCR, that has three terms which are corresponding to L, C, and R. Basically, one due to the R resistance, other due to the capacitance, and another due to the inductance. So all these three quantities, all two pairs from these will actually give you different time scales. So that's this problem is about. You have to identify which of them involves the time scale in the problem. Okay. So, right. Okay. So that's what it is about. We have to see whether L and C have the dimension of time. Hi, Diksha, can you turn on your mic? Yeah.
Yes, sir. Hello, sir. Very good afternoon, sir.
Yeah, yeah. So, do you have any doubt from this week 4?
No, sir. Actually, I haven't done the work of this week, so I just had to cover up all this in this weekend. So I'm
Okay.
here to interact with you, sir.
Okay. So, I have already done two problems, and those were related to solving the differential equation. So, you know about how to solve differential equations, right?
Right, sir.
Yeah. So what we normally do, we normally use different methods to solve differential equation. Like for example, you write the characteristic equation by assuming some solution, general solution, for example, e to the power rt. Then you write the characteristic equation in that parameter r, and you solve for the roots of this equation. And based on whether they are complex, real, and you write the general solution as a linear combination of those possible things, right? Now, those kind of things are the analytical way of solving this equation. But in Mathematica, you feed in the differential equation, you use the inbuilt function dsolve, and you just are able to get the solution of that. So this is what I did before that. I'll just show you what I did before. So this was the problem one from the last year assignment. So if you see, this is a differential equation, second order differential equation, the second derivative written in terms of the just x and the first derivative. Okay. So ideally, what would you do to solve this problem? You would assume the x is e to the power rt, and you write the first derivative, you write the second derivative, and you get the characteristic equation like this. You solve for the roots and you write the general solution and use the initial and these conditions to get the final solution. So this problem could have been done analytically. But what our idea is to see how you would solve this using the Mathematica. So I did it, but you were not there. So let's do it again. So, right. Yeah. So I would say okay, what is this? Let's open a new notebook. Perfect. So you must know about NSolve.
Yes, sir.
So similar to that, that was to solve the system of linear equation. Similar to that, there is a D-solve. And if you see the syntax of that, you can just click this. And you would see the syntax is, if you go to the details and option, these kind of equations you can have u derivative is equal to f of x comma u. So this is ordinary differential equation. There could be a partial differential equation, and there could be any kind of basically the differential equation. You can solve this using dsolve. So now in our case, what our differential equation is, it's x double derivative. You'll write t as the variable, equal minus x of t minus square root of 2 into x of t. That's the thing. But we have initial conditions also. So I'll put a curly bracket and specify initial condition as well with this, which is x of 0 at time t equal to 0 equal 1, which is given to us. X derivative at 0 is equal 0. I'll close this. What I want x of t. What is the independent variable? T. That's the syntax. And you close it. You solve this. You get the solution. Okay, this is not what I expected. Why we got the wrong one? Because we forgot to put the derivative over there. Yeah. Yeah, so this is a solution. Now, if you see, this is something which is not in the option. So basically, you have to simplify each of the option to see which one matches. And what you can do is you can take any option. For example, C is the correct option. I mean, you have to take every option and see. Let's say I'll write C option, square root of 2 into exponential of minus p by root 2, which is square root of 2, I'll close it, cos of t by root 2, square root 2 minus pi by 4. This is a C option. I'll subtract the solution. Sorry, this is in the solution. So this solution, this thing, I'll take the first of that. First of solution basically, or you can just say solve ka first element. Yeah, oh sorry. Yeah, I'll just take this. Yeah. So let's see. And if I say simplify, what will it give me? Should give me, oh, there is a syntax problem. Um, what is the issue? Right. So it's the x of t ka. So this is x of t, right? So you have to say x of t ka first argument, which is this solution, this thing inside it. So it has to be close brackets this. I think this would give me 0. Yeah, it gave me 0. So if I would have used the first option, it will not give me 0. It will give me something else. So basically C is the correct option. Or what you could have done, you have this thing, you have the solution. You could have just simplified it in terms of the forms in which it is given in the solutions, like this way. You do it for every of this. Basically cos A plus B, you use the formula and you will get the correct thing. So is that clear? First problem? Diksha, do you have any doubt?
No, sir.
Okay. So the second problem was also similar. It's just that if you see the differential equation is x dot minus is equal to minus xt. So if you solve this analytically, it's nothing but variable separable form, and you find the general solution using the initial condition, you get x is equal to e to the power minus t square by 2. But that's not our aim. We have to find it using the Mathematica. Okay, right. So if I see this one, I did it. So what we will do is I'll just change it over here. T, let's just remove this. And Initial condition is same except the derivative. Hmm. I'll see. I'll just rerun it. Okay. Oh, this was not first derivative. You got Aries function, right? If you do it second derivative, which is what no, we don't want. It's the first derivative. Huh. So it's e to the power minus t square by 2. It gave me the solution. Now I could have just plotted it. Um, let's plot it. Plot. For that, first I will have to extract this thing. So it's xt sol xt is equal to, let's say, x of t sol, which is 1 1, the first element. So I have extracted the solution out of this association, and now I'll plot this thing. Plot xt comma, the scale is from 0 to 5. That's what this problem says. Now you can add all those labels and all. Let's not do that as of now. So this is the solution. And if you look into the options, which one seems to be more? Um, it's the B option. Okay. So next problem is about dimensional analysis. I don't want to waste that time on that one. It's basically writing the units and then equating all this stuff and you'll get the dimensions correctly. So as of now, we won't waste the time, but we'll move to the one which are computationally we have to solve. For example, this problem. So this problem says for a spring mass system moving on a surface with non-zero but small friction. Basically, there is damping, but it's underdamped. They're saying it's not how overdamped. So there are three cases: underdamped, critical damp, and overdamped. So they're saying there is a small damping in the system. In that case, how would your amplitude decrease as a function of time? This problem can be solved by analytical way also. Let's solve that first, and then we'll see how this becomes very simple if you just have used Mathematica. So let me add a page after this. Just a second. Okay, so let's do that. Uh, yeah. Okay, so what's the differential equation of the spring mass system? Diksha, do you know what's the differential equation in terms of mass, spring constant, and the damping factor, B? Any idea? Okay, so it's basically this force term, M.
Uh, Sir, it's omega is equals to under root k by m.
That's the frequency. But what is the differential equation? That's true. What you said is right. That's the frequency of the oscillation. If you have no damping, basically m x double bar is minus kx. So that's the differential
Uh,
equation.
yes,
When
sorry, sir. It's I guess d square x by dt square plus omega square xt is equals to 0.
exactly that is
And the
for the
general solution is xt is equals to a cos omega t plus phi.
perfect.
Yes,
That
yes.
is for the no damping. But now we have damping also. So damping term is proportional to velocity, which is x dot, and that proportional constant is b. So just not this term, there would be additional term minus b x dot. So the overall differential equation now becomes mx double dot plus bx plus kx. What you said was without this term because there was no damping. Now we are considering a damped system. So this is the differential equation. Okay. Now we'll assume the general solution e to the power RT. And if I do the derivative of this, this is e to the power mr square plus br plus k e to the power RT equal to 0. This is greater than 0 always. So that means this has to be 0, which means your characteristic equation is mr square plus br plus a equal to 0. Now using quadratic formula, you can write minus b plus minus b square minus 4mk by 2m. So it's b minus b by 2m plus minus, I can say b square by 4m square minus k by m. I think that's right. Yeah. Okay. So this means if I assume b by m 2m, let's call it gamma, and this we can call it some omega damped one, which is nothing but, it's nothing but something, let's call it, because this is gamma, so it's gamma square minus a by m was what? It was the undamped frequency, omega naught square. So I'll call it omega naught square. So this is how I have defined my parameters now. Perfect. Let me add page after. One more page because this is a long derivation. Perfect. So now what my solution will be? So R is nothing but minus gamma plus minus iota omega damped, where omega damped is gamma square minus omega square, omega naught square. Perfect. So the solution would be x of t e to the power minus lambda t times c1 cos omega dt plus c2 cos sine omega dt. I hope this is clear, right? Because let me just clear it to you why it went this. Since we assumed the general solution e to the power rt. So there are two solutions to the r. One is this minus gamma plus iota iota omega d. Other is minus gamma minus omega iota omega d. So I will write it as a linear combination. So let's say I write it as gamma plus iota omega d times t times a plus b e to the power plus I omega t. So this is basically minus. Okay. So then I'll take the gamma t common, e to the power minus gamma t common. It would be a e to the power minus I omega dt plus b e to the power I omega dt. Now this I can write in terms of cos and sine. This also I can write in terms of cos and sine. Keeping the constants together, you will see C1 would be a C1 would be a plus IB, no, a plus B, and the C2 would be IB minus A. So you'll get the final solution as this. Okay. So this is your final solution. So if you can write it in another form by using the cos and sine rule, you can actually go to this as well. That's for you to see. So it's basically this, the general solution. So there are three parameters, two independent A and Y, and two depends on the system, which is this gamma and omega t. Okay, this is our general solution. Now let's see question. What does problem says? Go back to the problem. Problem wants us to see how your amplitude varies with time. So what is the amplitude? Anything except this oscillatory term is the amplitude. So basically your amplitude is a function of time as this. Okay. Now they say for the small damping case, basically gamma is b by 2m. So when b is much, much less than the mass. So basically when b is very small, in that case, how would this vary? Analytically, you can say it's a Taylor expansion. So it will be nothing but 1 minus just linear term. Because gamma is small, so other square and other cube terms will go to 0. So if you can see, this is nothing but it is decreasing linearly with time with the slope, which is directly proportional to the damping factor. You know the answer now. What is the answer to this problem? It's option A. But we could have seen this just using Mathematica instead of doing this complicated derivation. So let's do that. So what you really need to do is, uh, okay, yeah. What you really need to do is you just have to solve the differential equation, which is, so for that, before that, let me define some parameters. Let's say mass is 1. Let's say omega is, the k is also 1. Since b has to be small, let's define it as something very less, which is 0.0045 or something like that. We'll see, we would have to make it even much more less to make the it go to very small limit, basically almost negligible damping. So let's start with this. Okay, so now your parameters have been defined. So I will use solve. There is a function ndsolve. Now, why are we using this function? Let's go to the information. Whenever you're confused about something, just go and look there. So, so it's basically, why are we doing this? It's basically give us the function, not just the differential equation solve. It's also give us the value of the solution at all the values of the independent variable you define. In this case, our independent variable is time. Okay, so in dsolve will give you symbolic form of the answer, which would be e to the power minus gamma t cos omega dt plus phi. But I don't want that. I want a list which has the values at all the times I define in the function. So that's why we are not using dsolve, but we are using ndsolve. So it will give me basically the numbers at all the time intervals. Rest syntax is same. So I'll put the differential equation inside. So m times second derivative x double t. Okay. What was the another term? B times x first derivative t. Okay. Plus k times just xt equal 0. Initial condition are given to us. Let's say our initial condition is x0 is 1. It starts from 1. Let's say x, the velocity is also, uh, velocity we should start with 0 because, yeah, it will be 0, right? Because it's a, sinusoidal function. So if the this thing is 1, so your velocity have to be 0, or it can be anything actually. You can start with any number, doesn't matter. We'll try to change and see. So what do you want out? X of x, which is our quantity, and what is the time interval? That's the extra thing you would have to specify. That's what you see here. X comma x min comma x max. So you define the u, which is u in our case is x here, and x in our case is t here. Okay. So you see, I am exactly following this syntax. Equations, u, and the range. So t goes from, let's say 0 to, I say 50. Let's start with that. Okay. ND solve. Okay, that's fine. They have given me this basically a function, but I don't want to do that. I just want to plot the thing. So what I will do, I'll extract this solution as some function, which will be using, it will keep changing every time it evaluates at the. So you should know what is the difference between the evaluate. I want to evaluate x of t dot solution, which is this interpolating function. From this association, I want to extract this thing. That's what I'm doing. Okay. Right. Um, Okay. Now I will just plot this. Plot whatever we have extracted from this association. Plot x sol t comma at with watch range t0 50. Okay, that's it. We don't want to put any plotting styles as of now. So let's just see. Huh. So you see, you got the plot of the solution as a function of time. Right. It plotted till 40, but I could have changed it to 50. That's okay. So if you see here, the trend is linear. It's approximately linear, but after that it's little curved. That's why, because we haven't used much smaller value of this damping. Let's reduce it more. So if you see now, it's very linear decrease. So, but if I would have taken larger value, you won't see such decrease. 0.5, let's say. The damping is basically of the order of the elasticity of the system. Okay. Okay, I would have to do the plot range. I would set the plot range, let's say, yeah, so plot range all, let's say. Huh. So if you see, I did the plot range all. Uh, you see, it's not linear. It's like this, and then it's little curvy. It's not going like linear. So, right. I hope this is clear. Okay, perfect. Right. If I make it zero point 0.3, yeah, it's not linear at all. Let's go to 0.1. So yeah, our claim is this becomes only linear as it becomes very small. The b becomes very small. So in those cases, it will be linear, right? So that we have seen. So our correct option is it decreases linearly with time. Okay. And I've given complete solution in the attached sheet. You can go through that. Now let's do another problem, which is about the solving this differential equation. Hi, Diksha, do you have any doubt?
No, sir, it's clear.
Okay, so the I explained why it is decreasing linearly with time. So that's the idea of the problem, just using the Mathematica code, and you can see that this is linear decrease, this thing. Okay, fine. So let's move to the another problem. Let me do this one for you, which is Euler method. So do you know Euler method? Diksha, do you have any idea about Euler method?
Yes, sir.
Okay, so what that really is?
Uh,
It's basically how do you define derivative in the terms of just discrete differences. Do you know that definition? So definition of derivative, let's say dx by dt is what? Its limit h tending to 0, x at t plus delta t minus x at t by delta t. Okay. Now, if I just remove the limit as of now, sorry, delta t tending to 0, if I remove just limit as of now, then what it would be? X t plus delta t is nothing but xt plus dx by dt times delta t. This is nothing but Euler method. So this holds only when your delta t is very small. So what the idea of Euler method is, if you want to solve a differential equation which is like this, what you would do, so I'm at, let's say, time t equal to 0. I want what is the value of time t equal to some t naught. So what I will do, I will divide this line into very small grid points. Okay. So that is our delta t. I'll first update, start from t0 and first update by this delta t times the derivative of that point. Then I'll take start from there. Then I move to next point. I'll keep doing like this and I'll reach the value at the final point. So that's how you solve the differential equation using Euler method. So that's what we are gonna do now in the computer. Okay. So you see, I have given this code in the presentation which I will be uploading, and you can go through that. I will also just solve it right away. How would you write that simple code? So that's the idea. Okay, so let's do that. So our differential equation was, if I show it again, it was this. X dot is equal to 4t plus 3x. And this is the initial condition. Okay, and they are saying, yeah, you use h equal to 0.3. So basically the interval you will be using is h delta t would be using is zero point 0.3. Okay, so let's do that. You could have solved this equation using the ND solve as well. Okay, but that's what we know the problem doesn't want now. It wants us to do it using the Euler method. Okay, so let's do that. And it wants us to calculate the value x3, basically the third interval. Number of steps are 3. So let's define the parameters initially. So let's say h, which I have supposed to use, is 0.3. Perfect. The x naught is given to us. It has to be 1. Perfect. T naught is obviously 0. You start from the 0 time. And your n number of steps are 3. Okay. So what I will do, I'll first define a table which stores the value of the what are the i's basically. So let's do that. X values equal to, table would make a list basically of what? 0 comma I from 0 to n. Now if you print this, you will see it is nothing but x. So your this has been defined. H is this, x naught is this, t naught is this, n is this, and your table is this. Okay, so initially you have defined a list which has 0 values. Okay, initially it has 0 values. Now what I will do, I will say the first value I will have to put it as x naught equal to 1. So what I will do, this x values list ka first value, which is this, has to be x naught. Okay, now what I will do, I will print the sorry. Okay, what just happened? That's okay. I'll print the x values again to see whether the first element in this list has been modified or not. You see, the first element has been modified. So your t equal to 0 step x value is this. Now we'll run a loop, and in the loop, we'll keep changing our x at later steps, basically x at 1, x at 2, x at 3. by Euler method equation. And this is the final is something which we want. Okay, so let's write that loop. I'll start the loop. So which the condition is x values at I plus 1. Basically I plus 1, and I will define how the I has to go in the list. So I plus 1 has to be equal to x values at I plus what? The derivative, which is what? Which is in our problem is what? The derivative is what? It's x dot, and which is 4t plus 3x. So it would be, it would be uh, f of, we didn't define any function before, right? I could have defined function before, or yeah, we can just write, let's say 3, 4t plus 3x, right? 4t, and t was what? It would be nothing but ri plus 3x. Um, right, it has to be, t naught is this, it has to be, sorry, it has to be, I could have defined t values also before, right? Mm, let me define a function before we go there. Okay, let's remove this. So I'll define function as x comma t is equal to 4t plus 3 comma x. Okay, or let's not define function, let's do it straightforward. It's not complicated. Do what do we have to start with? Our condition, which is x values at I plus 1 equal to x values at I plus h times, which is zero point 0.3 we will be using, h times our 4 times um, t naught plus, we have to update it by I minus 1 into h. That is fine. Plus 3 times uh, x values, which is x values at ith point. That's the recursion in the loop. And I will close this bracket first, then I'll close this bracket, then I will close the do loop. No, I'll put the in condition for I, then we will close. So I starts from 1, 2, 3 step. Then we will close this thing. I think that's good enough. Okay, it ran. This ran. Now what I want to print? I want to print x values at fourth value, basically n plus 1. N plus 1. Let's see, what do you get? 8.263. So basically, if you print the x values now, you will see a list has been modified. Initially, we started 1, then you use the Euler method. It updated to 1.9 according to the differential equation. It updated to 3.97 in the second step. It updated to 8.263 in the third step. Is that clear, Diksha? This basically this part you have to be very clear where you are putting the function.
Yes, sir, it's clear.
Yeah, perfect. So in solution, I have done a little different way, the solution which I updated. So I'll change that. So there was a mistake over there. I just realized. So I have written a function and I didn't put the screenshot of the where I have defined this function. So either you could have done by predefining the function f square bracket t comma x as 4t plus 3x. Or if you don't do that, you just update the things in the 4t plus 3x like I did in this problem right now. Okay, so that was another problem. Right. Now let's do some theoret. These were all the computational one. Now let's do some theoretical problems like this. Okay, so this question is about in improved Euler method, how is your local error in terms of the step size? So do you have any idea about improved Euler method?
No, sir.
Okay, so this was actually taught in this week, fourth week thing. But if not, and this was done in the lecture, but we will do it again just for your purpose. So the problem wants us to find the estimate what would be the order of the local error. Basically, it's h1, h square, h cube, h to the power 4, or what is the order of this error basically. So for that, first we should define how this modified Euler method work for a general set of differential equation. So let's write the general differential equation. It's dy by dt in terms of f of t comma y with y at t equal to 0 equal to some y naught. So this is the equation we want to solve. Now what improved Euler method do? What we would have done in standard Euler method? You would have done y at n plus 1 step is y at n plus h times f at tn and yn. That's your normal Euler method. But in the improved Euler method, it's not that. They take an average of the slopes at two different points. So basically they replace this by h by 2 plus some f at two different points, point 1, f at point 2. Now, what are the points that they take? They are, one is same, which is t of n, y of n. Another is t of n plus h, comma y of n plus h times f of t of n, y of n. So it's basically, if I draw it in the terms of, let's say this is our function. Okay, at t of n, this is my y of n. Okay, now they take another point which is updated by t of n plus h. They take the slope at this point and then multiply with that slope, which is basically h times f of t of n, y of n. So, right. So in modified Euler method, just a second, add page. Okay. Yeah. So in modified Euler method, your differential equation solution is modified like this. Y of n plus n h by 2 f at p of n comma y of n plus f at t of n plus h y of n plus h time f of t of n y of n. So this is the modified Euler method. Now, simply we have to find what is the error basically estimation. And that's very simple to do. What we will do, we'll simple do the Taylor's expansion of this term. Because Taylor expansion is something which will give us the error estimation. For that, first do y of n, y of t of n plus h would be what? Because our f of t n plus h is what? It's yeah. So that's what we will do. So it's y of n at, sorry, y at t of n. What is the Taylor expansion? H y of derivative t of n, h square by 2 y second derivative at t of n, cube by 6 y of third derivative t of n. Let's write other order as just this. We might need them later. Okay, now I'll substitute the y derivative of t of n by f of t of n y of n, because our differential equation was what? Y derivative is equal to f of t comma y. So that's what I will be doing right now. So this will make it y of t of n plus h, y of t of n plus h times f of n, basically this point. Second would be h square by 2 y double derivative, which will become f derivative n plus h cube by 6 f double derivative n plus order h4. So this is our condition now, where your f of n was f of tn yn, f of n derivative was d by dt of that at tn yn, f of n double derivative was d by dt square of that tn yn. Perfect. Now let's substitute these things in the modified Euler method. So basically, our thing was f of tn plus h uh, comma x yn plus h fn is what? Now if I expand it using the Taylor series, it is nothing but fn plus h fn bar plus h fn delta fy plus order h square. Okay, uh, just a second. It's getting little messy, but I have the full derivation uh, in the presentation, so you can go through those steps very carefully later onwards. So yn plus 1 is equal to yn plus h by 2. So there is a first term which is f at n, second term which is we expanded just now, fn plus h times fn bar plus h times fn del fn by del, sorry, del f by del y at n. Okay, plus order h square. Now, if I multiply this h inside, so this term will be also multiplied by h. So it will be overall order h cube. So that's what we had to estimate. When I am updating yn plus 1 after another step, what is the order of the error which is left? And you see, if you do the Taylor expansion the way we did, it's the order h cube which is left locally. So that's what the problem wanted in our case. Um, yeah, so the order is h to the power cube of the local error. So local error is basically the error which accumulates at every step of step size h. So overall error, what it would be? So it would be nh times this order h cube, right? So, so it would be basically, if there is an error of h cube, then your n steps is nothing but total time by h. So you multiply by t by h with order h cube. So h will cancel one. So overall global error will be h square. So if your problem can also ask you what is the global error. So in global error, it would be h square, not h cube. Okay, so this was the problem, and you can go through it carefully once I attach these PDFs in the slides. And you can, anytime you can ask me questions in your forum, I would answer over there as well. Right. So any problem with this estimation of the error? So all you need to do is nothing but Taylor expansion. Whatever differential equation is given to you and whatever method demands, like algorithm can be different. For example, there is another way of solving this differential equation, which is RK4, Range-Kutta 4. So this is another method where they just don't take these 2 points where they take the slope, they take 4 points, right? So then it would be sum of all these 4 points into h by 4. So in that case, if someone asks you to estimate the error, then you would have to do similar procedure at all these 4 points. You would have to do the Taylor expansion over there. And you would have to keep collecting the orders. And overall at the end, you would have to see what is the order which is left over there. And it turns out that Range-Kutta is even much less erroneous than this modified Euler method. So someone can ask you this problem. Yeah, so I'm just saying any general way of differential equation is given to you. All you need is to do the Taylor expansion to identify what is the error which will accumulate. Okay, right. So Diksha, is that clear? Whatever we did right now? Hi, Diksha, can you hear me? Okay, fine. So you can understand this thing, which is good. Anyways, I will also be sharing the slides, which is okay. Let's do some other problems. So there are these problems related to dimension. So this won't require any Mathematica for you, but let me do it for the completeness for you because these kind of problems will be asked in your assignments. Okay, so the problem says, which of the following are the dimensionless quantities of a system for which the differential equation is this? Basically, the equation of motion is this. So there is a theta double dot. So it could be a equation of actually pendulum. Why theta space? Because in pendulum, what happens? It's when it is rotating like this, you basically look how the theta is changing with time. So it could be the equation of that kind of system. So they say it is theta second derivative is equal to minus alpha sine theta plus this kind of equation. So all you have to do in order to identify the dimensionless quantities is first you have to identify what are the units of alpha, beta and gamma. And how that you will identify? First you would see theta double dot. And you know theta double dot has the units of what units? It's nothing but uh, time minus square because it's d square theta by dt square. Okay. So I will equate this to the first term, which is minus alpha sine theta. Okay, sine theta is dimensionless. That means your alpha will also have same dimensions as t power minus 2. So first you identified alpha has t power minus 2. That's first thing. Next thing now, you equate it to the second term. So t power minus 2 is equal to beta time theta dot, which is t power minus 1. So your beta has to be t power minus 1. Okay, you get beta also now. In third case, it's t power minus 2 is equal to gamma times t power minus 1 times t power minus 1. So it's basically gamma is nothing but t to the power 0, dimensionless. So the first correct option is clearly gamma. Right. First correct option is clearly gamma, which has to be dimensionless. Okay. Now they say what are the other quantities? So let's say alpha. Alpha is clearly not dimensionless. Beta is clearly not dimensionless. Beta square by alpha, let's say. So beta square is t minus 1 square, t minus square, it cancels, it is dimensionless. Gamma square by beta. Gamma has no dimension, beta has dimension, so this can never be dimensionless. This and this, these are the two only correct option. Right, so that is clear. Similarly, you can do this fourth problem, which also deals with calculating the dimensions of the system. Okay, we did the improved Euler method thing as well. Okay, this we did. This LCR circuit may when is it's the critical damped case. Okay, so let's just do it once. So this is your differential equation in LCR. L d square q by dt square r dq by dt plus q by c. So if I assume q as some e to the power lambda t, it would be characteristic lambda square r lambda plus 1 by c. And if I just solve this equation like this, it would be this. Okay, now if I just solve this, and for critical damping case, what the condition has to be, your this has to be 0. So that means r square minus 4l by c has to be 0. So r square c by l has to be 4. So your D is the correct option. So yeah, there are some simple questions over there which you can solve. Now there is this question which is also very simple to do. Let's do it over the Mathematica. Okay, let's do it. Sorry. Yeah. Huh. So let's write the equation equal to, it is theta double prime P equal minus 2, and I'll write theta again. So this is the equation you have written now. Now I'll define the solution, which is using T-solve. This is the equation. What I want, theta, my t, independent variable t. Okay. So this is the equation. Now you can clearly see the first term, it's a linear combination of e to the power minus t by 2 cos square root 7 by 2t, and another is e to the power minus t by 2 sine square root 7 t by 2. Okay, so if you look at the options now, look at the options. Yeah, so it's clearly option number A and option number B, right? So that's the correct option which you have and which you solve using Mathematica as well. So I think from my side, we have done 10th problem as well, 9th as well, and this as well. Yeah, we have also estimated the error. Perfect. We have estimated this sixth problem as well, fifth as well, and fourth as well. Yeah, 3 is basically the relevant timescales you can calculate. This is energy basically. So if you see this, what the question says, the rate at which average energy decreases in underdamped LCR circuit with instantaneous charge Q on the capacitor is of order of what? So it's energy, it's power loss, right? So which is power loss? So power is basically proportional to I square R. And you know I is what? dq by dt. And it is of the order of Q square by LC, right? So that's nothing but Q by square root LC. So if you see the dimensions of the system, there it has to be Q root by LC because it's omega. So Q into omega it has to be, right? So Q by square root LC. So your power is I square R, which has to be Q square R by LC. So that's the rate at which the energy should decay. So option A. Perfect. Now this one could have done by defining the units of L, units of C, and units of R as well. One could have done in that way as well. Okay. So right. So yeah, that's what we really wanted. I think that's all we had for today. I did all the 10 problems from the past year, which involved using the D-solve, which involved using the ND-solve, which also in some of the case involves just using normal functions to get the dimensional analysis. And for some cases, it requires the loop where it requires the do loop. You could have used for loops as well. No issues with that. While loop, anything you could have stopped after 3 steps. Okay. So you can practice it by using different loops. And we also estimated the errors. And there was one with the Euler method problem and one with the modified Euler method. So you can be asked these kind of problems in your later assignments. That's it. So I'll wait for 2-3 minutes for people to join in so that they can actually ask me questions if they have. Let's wait for 3-4 minutes. If someone is joining in, we can discuss the queries and yeah. Okay, so we have the feedback. I need to complete last week task before joining. I'll catch up soon. Okay. Okay, fine. So it was good to see that someone is understanding it very well. Yeah, that's the idea of this session. You should be able to understand even the difficult of the problems, which I mean might not be explained in that ways in your colleges, which is totally okay. So you can always ask me in any time in your forum. I will be able to answer the queries, everything. Okay. So thank you, Diksha. Bye. I think yeah, that's all we have for the today. I'll wait for 2-3-4 minutes if someone join in and we can answer their queries as well. Yeah, that would be great. I think we can actually end the session here. So it was very fun session today. We could interact very well today. So that's the idea of this session. Okay, these videos will be always available on the YouTube lecture series channel, and the YouTube links are put in the Google Sheets. And the presentation, whatever I presented, whatever I scribbled during the course, will also be put it in a PDF form in the presentation link, so you can go through them as well. And you are always free to ask doubts to my email, to the discussion forum. I'll be able to answer over there as well. Okay, thank you. Let me stop sharing my screen. We'll stop recording. Stop. Okay, I'll